Hey folks, Mr. Vass here. Have a little quick demo for you of a new technique for looking at definite integrals as a limit of a Riemann sum. First thing I want to do is show you this problem. Bang, there it is. This is a multiple choice question. It's one off of the practice AP test for the 2016 course description. And take a look at this. This is something we've never even touched this before. We've talked about definite integrals, and we've talked about how definite integrals are a limit of a Riemann sum, which maybe this is, who knows. How on earth are we supposed to answer this question? Hopefully you can dry your paper off, because I'm sure right now you're shedding a few tears because this is a frightening problem. Right now we have no idea how to do this, but I promise you within the next 10 to 12 minutes you will know how. So, how are we going to do this? First thing we're going to do is take a look at the notes page I put together for you guys. And I'll zoom out here so we can see the whole thing. Before you go any further, you should stop the video and you should read this from top to bottom, because it tells you everything you need to do. In fact, when you get down here, I got some steps here for you to actually to rewrite a definite integral as a limit of a Riemann sum. So go ahead, pause the video, and pick it back up here in a minute after you've read this. No, seriously, read it. Please read it. I went to all that trouble to put this thing together for you. I need you to read it. Okay, thank you for reading it. Now let's move on. One of the other things you have in addition to this page is a couple sets of problems. There's this one, says practice match each of the following limits to its definite integral. So here's definite integral on the left, and one of the limits in the right hand column matches this. There's a little bit of room in each of these boxes for you to work out some things, and perhaps in a few minutes you'll see what you would even work out. And then on the back side of this, you're going to see the following. Match each of the following limits to its definite integral. It's kind of the reverse of what you did before. This time you're given a bunch of information here about a bunch of different limits, and you have to pick the definite integral that matches it. So it's kind of the same process, just working backwards. Okay, so let's actually do one. Because you've read that whole procedure on the front side of page 1, I'm not going to go through that step by step. I'm not going to reread it to you, but what I am going to do is show you the nuts and bolts of what you need to know. Right here is the nuts and bolts of what you need to know. We are going to take a definite integral, and we're going to look at it as a limit of a Riemann sum. Now this is the definition. This definition is similar to the one that was in your textbook. We're going to switch it up a little bit and use it like this because it's a more convenient form for us to write this as one of these. Okay, so what is step 1? Step 1 is come up with an expression for delta x. And quite simply, delta x is going to be equal to b minus a divided by n, where b is our upper limit of integration, a is our lower limit of integration, and n is the factor. It's the variable that we're taking to infinity in our limit. So this is going to be, for this problem, 2 minus 0 over n, which we'll rewrite as 2 over n. So there you have it. That's delta x. We're ready to move on to step 2. I just want to mention one thing before I move on here. For these problems, we're not actually going to be evaluating the limit. Why bother? We know how to do the fundamental theorem, use the fundamental theorem of calculus to evaluate a definite integral. We're really doing this just so that when you go off to college and your professor says that a definite integral is the limit of a Riemann sum, you can say, oh yeah, I remember Mr. Vass talked about that one day. The other reason we're doing it is because it could show up on the AP test, and I want you to have as many tools in the toolbox as possible. Okay, so we found delta x. That's great. What now? I want to give you a little warning. Okay, in a minute you're going to see another parameter k that's going to be introduced to this problem. You shouldn't have a k in this. And the only reason I'm telling you this is because a lot of times when I do these practice problems, I end up putting a k in here, like right there, and then it's wrong. So because I made that mistake, I want to try and help you not make the same mistake. Don't add k here. There should be no k there. Okay, we're going to move on to step 2. Step 2, we will see a k, and what we need to do is come up with an expression for a plus k times delta x. So in this case, we have a, which is our lower limit of integration. K is an index for our sum. And then I have to multiply by delta x, which is 2 over n. Okay, so this we can simplify to just 2k over n. Okay, so maybe now you see why I was tempted to put a k up here, because these two things look very similar. But they are different. Okay, so step 3, what we're going to do here is we're going to actually do some substitution and come up with an expression for the following. F of a plus k delta x times delta x. So for this example, we have f of x equals x squared plus 10. So let's go ahead and substitute a plus k delta x in for x squared. So a plus k delta x is 2k over n. We did that in the previous step. We need to square that and then add 10 to it. Then we have to multiply by delta x, which, as we've already discovered, is 2 over n. Okay, so let's do a little bit of simplification here, but not a whole lot. What I'm going to show you is I'm just going to square this term right here, so that's going to become 4k squared over n squared. I have to add 10 to that, and then I have to tack on my delta x here at the end. And I'm going to stop right there. And the reason why I'm going to stop right there is because in this form you can still see the f of x portion of the Riemann sum as well as the delta x or dx portion. So you can still see each of those components. The steps in the notes page were numbered 1, 2, and 3, but the fourth step is really just to write this in the Riemann sum notation. So I'm going to go back and write my original definite integral. It was the integral from 0 to 2 of x squared plus 10 dx. And this now equals the following. It equals this thing right here, except I'm going to substitute in this for the right hand side after the sigma notation. So this is the limit as n goes to infinity of the sum from k equals 1 to n of 4k squared over n squared plus 10 times 2 over n. That's your final answer, folks. Congratulate your neighbor, because you just successfully solved a problem where you had to rewrite a definite integral as a limit of a Riemann sum. This happens to be the first problem on the worksheet that I showed you back here. So this one is complete. Go ahead and find the matching Riemann sum on the right hand column. Let's do another example. Here we go. This is actually example B. We have the definite integral from 4 to 6 of 2x squared dx. F of x for this guy is 2x squared. Again, I'm going to pull this out here because this is actually what we're doing, what we're trying to do. Rewrite the definite integral as the limit of a Riemann sum. So I'm going to use the same steps I did before. I'm going to start with delta x equals b minus a over n. In this case, I have 6 minus 4 over n, and that's 2 over n. Hey, that's the same delta x as we had in the previous problem. Coincidence? I think not. It was in the previous problem, our limits of integration still had a delta x of 2. But what we're doing here is we're splitting it up into n subintervals. And then through the limit process, figuring out what the definite integral equals. But that's more than what our scope is for this lesson. Next thing here is we're going to come up with an expression for a plus k times delta x, Well, this is a little bit more challenging because this time our a isn't 0. Our a is 4. So that's going to make our algebra a little bit more complicated here in a second. So we have 4 plus k times 2 over n, which equals 4 plus 2k over n. And when I say 2k, that's not to be confused with the Xbox or PlayStation video game. Okay, so we have our delta x. We have a plus k delta x. We're ready to move on to step 3, which is to come up with an expression for f of a plus k delta x times delta x. In this case, my f of x is 2 times the quantity x squared. 2 times the quantity 4 plus 2k over n squared. And then I have to multiply that by delta x, which is 2 over n. All right, folks, here's where the algebra gets a little more complicated. I'm kind of, because I've squared a lot of binomials in my time, I can do this in one step. You may want to write it out in a couple. But I'm going to start by putting that multiplier of 2 down, and I know I have to square 4. And then I know I have to double 4 times 2k over n. That's going to give me plus 16k over n. And then I have to square 2k over n. That is going to give me 4k squared over n squared. Then I have to multiply that by delta x, which is 2 over n. So the only other simplification I'll do here is I'll distribute the 2 to everything. So we'll rewrite this as 32 plus 32k over n plus 8k squared over n squared. And that whole thing is multiplied by delta x, which is 2 over n. We are almost done. The last thing we have to do is write this as a limit. So the last part is the easiest. We're just going to rewrite our original integral. We had the integral from, what was it, 4 to 6 of 2x squared dx. And that now equals the limit as n goes to infinity of the sum from k equals 1 to n of 32 plus 32k over n plus 8k squared over n squared times delta x, which is 2 over n. Boom. Pat yourself on the back now because you've now done 2 of these successfully. Okay, so go ahead and take a look at the problems you had in that handout and see if you can't find out which one in the right-hand column equals what we just came up with. Okay, let's look at one more quick example. Oh, hey, this is what we started with. This is the original multiple choice question that brought some of you to tears. Which of the following integral expressions is equal to the limit as n goes to infinity of the sum from k equals 1 to n of the square root of the quantity 1 plus 3k over n all times 1 over n. So this one is actually, I think, really easy now that you've seen one of these examples. The key to this problem is right here. That's our delta x, which equals b minus a over n. If b minus a is 1, that means we have to find a definite integral where the difference between the upper and lower limit is 1, and there is only one example like that. It's right there. So the answer to this question is A. Let's move on. Oh, hey, we're moving on. We're done. So that's it, folks. We're done with this mini lesson. Hopefully, between the written notes that I have for you and a couple examples, you're able to work through all these problems and you feel more comfortable if you get one of those multiple choice questions on the AP exam. Thank you for watching.